My name is Matt Perry. I've been working, sort of in this field of data-intensive applications for over 15 years now. So my background is environmental science and geographic information systems, and so some of that will be reflected here. But in the last few years, I've really focused on sort of building core data technology, which is what brought me to Timescale last year. And so these days, I've been working more on solutions for time series applications, helping our customers with things like data modeling, performance optimization, and cloud architectures. So I hope some of those topics get covered in this. All right, so the system I'm going to show you today is about 2 months old. We started this in January. For those of you not familiar with New York City, the MTA is the Metro Transit Authority. One of the biggest bus systems, public transportation systems in the world, has thousands of buses operating at a time, billions of riders a year. So the animation that I'm showing here is 8 hours of a Friday workday, just of the M-Line buses, the buses running on Manhattan, and just gives a sense of sort of the scale and the complexity and the challenge of working with this sort of data, and maybe hints at some of the interesting analyses that we're going to get into. So the MTA, on the MTA side, they do a lot of great work, with the GPS technology on the edge, getting this stuff into a real-time API. The Mta Bus Time Api is a live feed of the bus's current locations, and it's all done through this specification by Google called the General Transit Feed Specification, or GTFS real-time. So just something to keep in mind while we are using MTA as an example here. This actually will apply to many other cities' transit systems that use this spec. So the Mta Bus Time API is a live feed of the bus's current locations, but we have, questions beyond where are the buses right now. Questions like, what's the hourly bus traffic historically for a route? What bus routes pass near a given location? Things that require us to sort of slice and dice data, filter and aggregate across space and time, look at historical and real-time data. So none of this is possible just with a real-time API alone. We need a spatial database and a robust query language to get at it. So this is the sort of the big picture of how the system is set up. Hopefully this is probably pretty familiar to anyone else who's running a time series application. You have sort of an ingest requirement, and this is sort of a near real time. We have this GTFS feed coming from the MTA that we're going to be pulling into our database. The database provides us temporal and geospatial data types. On the data management side, we want to be able to efficiently manage this stuff. We want to be able to set data retention policies to keep consistent storage requirements. We want to be able to look at, have consistent performance as the database scales, and we want to be able to, tune our queries and our hardware and our settings to our hardware. And then on the application side, we really need a flexible way to make geospatial and time series queries, both recent and historical, and we need to make them fast. And we don't necessarily know upfront what these things are, so we need a language like SQL that will give us the flexibility to sort of perform those on the fly. So like I said, most time series applications have this sort of general architecture. There's, these little, the data ingest side roughly maps to sort of data engineering concerns. Data management might be, the DBA side of things. Then you have the application side where you have app developers and data scientists who are pulling data from the database. The rest of the talk will go into more detail sort of about these different aspects of the overall system and sort of how Timescale can help from all these directions. So we're going to be considering the engineering challenges of all of these today. First, I'm going to give a quick overview of Timescale and what it is. And this will be a refresher if you've seen some of the other webinars or checked out our website materials. On the data ingest side, we'll briefly go over how we set up the data model and how we get data in. And then the bulk of the talk is going to be on the application side, how we write SQL queries to get at the data in the ways we need. And finally, we'll talk about some of the database management tasks and how Timescale facilitates those to keep our database running optimally. Quick jump into the into a refresher of TimescaleDB. You've probably heard the myth of SQL doesn't scale or relational databases don't scale. And this historically, has been rooted in some fact. This is something from our own documentation here showing against vanilla Postgres how Postgres will perform, pretty nicely at the beginning. Then as the database size grows, you sort of get this performance drop off after 200,000 rows or so. So the way Timescale gets around this is by treating time series data differently and by using some of the unique aspects of time series data to get both consistent insert rate over time and all of these speed ups over here on the right. And so what does it mean to adopt the structure of time series data, adapt to the structure of time series data? As far as we know, time only moves in one direction, or our experience of time only moves in one direction. In other words, the newer stuff comes next. So new data typically is appended to the front of the table. The partitioning in this case is handled automatically by Timescale, creating these new what we call chunks to store separate pieces of the time series data set. So in the Mta app, we have a chunk interval of 1 day, which means every day we'll get sort of a new chunk, which is a new table under the hood to put data into. What this allows us to do is frees us from the ability to, or frees us from the requirement to have a global index on the whole data set. We could have indexes that are local to each of these chunks, enabling things like query planner optimizations and parallel IO and all sorts of really neat data management tricks. You can take older chunks and put them on, slower disks or something like that. So there's really a lot of great performance characteristics that we get out of this partitioning. But it's not all about performance, of course. The user experience is really important, and that's the main, the hypertable is the main way we interact with this. It's a single logical table, looks and feels just like Postgres. Really, you don't have to, you get all this great stuff under the hood, but you don't have to worry about all of those details, nor do you have to throw away all the advantages of SQL. You still get indexes, joins, things like JSON data types and window functions and everything that comes with the Postgres ecosystem. And so the goal is really to make the hypertable look and feel just like a normal Postgres table, but have better performance characteristics under the hood. Some of the new features in Timescale 1.2 that was released last month that we'll be talking about today. Just real briefly, we've developed some tools for tuning the database, developed some time series analysis functionality that should help with a lot of cases, filling gaps, carrying the last observation forward, or LOCF, and interpolation techniques. And we've worked on what we call reordering, which allows a great increase in efficiency for certain types of queries, and automated data retention policies, which we'll get into later on. So on the data ingest side, let's take a look at sort of what we had to do just to sort of get this data in and start working with it. First things first, always tuning Postgres. I've spent a lot of years doing this by hand, and was extremely happy to see us release this last month, TimescaleDB Tune. This takes all the guesswork out. There's dozens of parameters in the PostgreSQL conf file that are, the database is fairly sensitive to some of them, and it takes a lot of the guesswork out to be able to run a tool that takes into account both the best practices in the Postgres community and what we know about time series data specifically, and your hardware. You see here we have, it knows exactly how much memory we have to work with and the number of CPUs, and can, based on those recommendations, tune our settings to be optimal. So this is really where we want to start for everything. Next was writing an application to get data into the hypertable. So I'm not going to go into the details of this, but we do have the code available on a GitHub repo, Timescale Mta-Timescale. Really, this is 86 lines of code, so it's not, this is nothing too complex. But if you have an interest in using Python with Timescale, you might take a look, or if you use Python with some of the GTFS data, it's worth taking a look at this right here. But I'm not going to go into too much detail, but happy to take questions later on this. So on the data model side, we see, a pretty typical data model here. We're loading up two extensions, Timescale and PostGIS. Timescale gives us the hypertable abstraction, which allows us to turn this MTA table into a hypertable. And then PostGIS gives us the ability to store latitude, longitude points, geometry. And so that will allow us to do geospatial queries. And of course, you have the indexes and all of the great indexing behavior and gist indexes and B-tree indexes and such that Postgres provides. So, the point here, I think the takeaway for me is that, it looks and feels very much like Postgres. We got all of the flexible data modeling. We can do, wide tables or narrow tables or JSON data types, and all of that flexible data modeling that we know and love about Postgres can be applied directly to our hypertables. So that is, that's the setup. We're streaming data in. The data is coming in, I think, at roughly 4,000 to 8,000 points a minute. So it's not a terribly high ingest rate. So that wasn't one of the significant challenges in our case. The challenge in our case is more, how do we get value out of the data once it's in? In other words, what are our applications going to do? So here is where, perhaps against my better judgment, I'm going to jump into some live queries. Just real quick to get oriented with the interface here. This is pgadmin 4, a pretty popular graphic front end to Postgres. On the left window here, you see my query. On the right, you see the data output, either as a table or in some cases as a geometry viewer, which allows us to actually map the data, which is mainly the reason why I chose pgadmin 4. It has this integrated geospatial viewing capabilities. Yeah, so now that we're oriented with pgadmin 4, let's dive into the queries. As we go through this stuff, I'm going to highlight or just point with my mouse. Hopefully y'all can see the mouse. But yeah, I will make sure to kind of walk through this stuff and point out the things that I'm talking about so we don't get disoriented here. The very basic starting query. This is sort of all the data for the last minute. This is a good point to jump in and take a look at this and just get familiarized with the data. Also, we see, hey, this actually is real time. We are we are pulling in data from 1 minute ago, right here. So this is all of the data for the last minute. We have a vehicle ID, which you can't see there. Okay, vehicle ID, a timestamp, the route that vehicle is on. So there could be several vehicles at a time serving one route. The bearing, just the direction it's pointed, and then of course the geometry. So if we want to look at this not in a tabular view, but in a map view, here's what it looks like. This is that same set of I think it was 2,000 some odd points from the last minute, and we can click on each individual one, get a sense of what's there at that point, and zoom in and out and get a little bit of context with this base map here. So it's a nifty interface. It allows us to sort of explore this stuff. But this is a select star query. The other thing to note here, we'll be using this pattern a lot. Time greater than now minus interval is another way to say, show me the last whatever the interval is. So in this case, we'll be using this a lot, this idiom a lot in some of the subsequent queries. The hourly count of vehicles on a given route. This is something that we want to use to sort of, I'd mentioned multiple vehicles can be out at a given time. This is a way to visualize that, or actually just look in and get the data for that. So the first thing we do is we count the distinct vehicle IDs. And then we want to aggregate that to what we call a time bucket. So this functionality has been with Timescale since before the 1.0 release. This allows us to aggregate our data to set time intervals. that we call buckets. So here we have an hourly bucket from the MTA table, of course, and then we are just looking here at, for 2 days worth of data, actually just 1 day, I suppose, 1 day of data, and for a particular route. When we run this, we get what we asked for, which is a count of the vehicles for each of the hourly buckets. You'll notice the problem here though. Between the hours of 1 a.m. and 4 a.m., we don't have any data. We don't, in this case, that route probably just is not in operation. The M100 route just isn't running any buses during that time period. This causes a problem with a lot of visualization techniques and a lot of analytical techniques where you expect sort of a contiguous set of time series buckets. And these sorts of gaps are not acceptable or need to be handled on the application side at sort of great expense to the complexity of the application. The 1.2 release of Timescale comes with, the community edition comes with a function called time bucket gap fill. This is our solution to that problem. Let me just run that again without highlighting. So this you'll see, despite the fact that we don't have any data for these time periods, we'll actually continue to include them in the results in order to get a contiguous set of evenly spaced time buckets in your results. But you notice the count is null. So depending on your application, there are a couple of different ways to handle these gaps. And this is where some of the other functionality that's released in 1.2 will help out. First thing, I'm just going to sort of uncomment these one by one so we can see the effects. So if instead of having a null in place where we don't have data, we wanted to actually put some interpretation on top of that. We want to say, okay, well, where there's no vehicles, we want to just call that 0. This is a count after all, so that makes sense. So we can run this and fill in those gaps with a 0. And so this is a very basic. The coalesce is a Postgres function, and very, very basic, allows us to sort of form that interpretation of the data. Another way we can interpret the data is, well, maybe the data was just missing. Maybe what we want to do is carry the last observation forward. So that's LOCF, last observation carried forward, allows us to do just that. It takes the previously known data value and carries it forward in the event of any nulls. So we see here, we just assume that there was 2 buses on the route in these hours because we didn't hear otherwise. And then finally, one way to do it is assume that the data is sort of continuous despite having no observations in that time period. And we can use a linear interpolation technique. So what this allows us to do, and this doesn't really match this too much because you can't have 2.6 buses on the road at any given time, but just to show you how you could, in cases where you're looking at things like temperature or other continuous values, you could really you could do some work with Interpolate to kind of fill in the gaps in the event of missing data. And so that covers most of what we refer to as sort of the time bucket gap fill type functionality. And so this is pretty powerful stuff. We can do a lot of the prep work and the data manipulation that's required for subsequent analyses and visualizations really effectively through this. Okay, getting into some of the geospatial stuff. I'm not going to focus too much on this code. This is all PostGIS functions here. So I just created a little PLPG SQL function called buffer meters, which takes a longitude, a latitude, and a number of meters and buffers the point out. So we could buffer this. This is the address for, or this is the latitude and longitude for 355 Madison, which is the Timescale office in New York City. And then we can take any sort of buffer distance, for instance, if we wanted to buffer it by 2,000 meters and take a look. Okay, that's most of Manhattan, east to west anyway. And then So this allows us to pretty flexibly change some of these parameters and to sort of do some geospatial data manipulation that allow us to do things like what we're going to see in the next slide. All right. So we see here this buffer meters, which is the function I just showed you. We put that inside of what's called a common table expression. This allows us to sort of separate out that result and treat it as a separate table later on that we can then join to our MTA table. Here we're doing another time bucket gap fill, so aggregating stuff to the hour as we did before. Instead of counting the distinct vehicles, what we're doing here is getting an array, creating the array ag function aggregates everything in it into a single array, into a single value. In this case, we're looking at the distinct route IDs. So this really answers the question, what routes pass near my location? And the near my location part is this st intersects. This is a PostGIS function provided by the PostGIS extension, which allows us to look at the buffer that we created up here in relation to the MTA geometry, which is a point representing where that observation falls. Where those intersect is within 200 meters of this location. So we're answering the question, what bus routes pass here? Oops, can't have that highlighted, can I? All right. So you see the results here. I did this over 5 days. So you can sort of see the ebb and flow of the availability of bus routes in this location. 5 o'clock, commuting hour, rush hour, we're looking at, many buses, and down in the wee hours of the morning, there's only one bus route running. So this is sort of what we expect. It's not a graphical representation by any means, but you sort of get a sense for the ebb and flow, the daily ebb and flow of the bus activity from this location, from the perspective of this location. And you notice also that there are some gaps in there, and the time bucket gap fill did its job by filling in those gaps so that we have a contiguous set of time buckets. Another way to look at geofencing is to look not at a buffer around a single point, but to look at where the bus geometry falls in relation to its prescribed route. And this is a really interesting query, because what we can sort of infer some things like, where are there traffic anomalies? In other words, if a bus is all of a sudden going off and skirting around a certain area, it might indicate that there is a traffic problem there, or construction that needs to be addressed in routing algorithms and things like that. So this is sort of like a early warning system for anomaly detection, or maybe just a way to look at how the buses actually work compared to their prescribed routes. So some of the things to point out in this SQL query. We're not doing any time bucketing here. We're just looking at, we're just doing a simple time filter, which is just saying everything in the last 15 minutes, we're looking at the M bus, the Manhattan buses. And we want to do everything that's within this bus geom is in the route geom. And the route geom is something I should explain. In the GitHub repo, I talk about how we downloaded the route data and buffer it out by, I think it was 20 meters to get sort of develop a polygon that represents the road and the route that the bus should be traveling on, and then look at it from the perspective of how many of those are not within that route. And then down here, I also union it with the routes themselves so that we can sort of see where the routes are and why, sort of get an intuition for why they might be off route. So running that query gives us a map. And this is not the greatest GIS software. It doesn't differentiate, for instance, between the routes and the points themselves too well, but gives you a sense. So I'll zoom in here on this particular one because it seems to be a pretty common deviation for this bus. The M35 bus, for instance, I think its prescribed route has it going up here into this sort of cul-de-sac and turning around and coming back by the same route. You see very typically up here at Hellgate Circle, we have the buses sort of doing this little turnaround a little bit earlier. And so that's pretty typical. In this case, it doesn't really represent a traffic anomaly as much as it does, this is sort of not a representative of the bus's actual route. But there's cases elsewhere which might be interpreted as traffic anomalies. For instance, some of these might just be buses that have gone off route for the purpose of getting around traffic, construction, that sort of thing. Okay, getting into some of the more performance-oriented stuff or performance tuning stuff. I have a pretty simple query here. This is not quite as complex of a query here, but this is something that something that we should look at. This is basically just counting the number of buses on a given route, or the number of observations of buses between a time period here. So I'm going to run that for the 6th, March 6th. And you see we have 1,700 buses, or 1,700 observations between that time period for the S86 route. Not very interesting in and of itself. What I really want to jump into here is the Analyse Plan. If you're using another interface like pSQL or some sort of text interface, you can use the explain analyze buffers command before your SQL statement. I'm going to do this visually just because pgadmin4 has a pretty nice little visual query explain tool. So running that, you'll see two things to notice. You see that one is we exclude all of the other chunks. In other words, this one chunk is all we touch, and there's several dozen in our database at this point. This is the only one we need to see because we know we're constrained to March 6th. We know exactly where the data for March 6th lives. We don't need to touch any of the rest of the hundreds of millions of rows that we have. The second thing, and this is the one that I really want to focus on here, is the shared hit blocks. Hopefully everyone can see that. But if you look at the shared hit blocks or the shared read blocks, this is a block is by default an 8K chunk of data that Postgres uses to store all of its rows. And this block can either reside, will reside on disk, but can also reside in our shared buffers in our memory area. Regardless of where it's living at the time, you have your performance is really limited by how many blocks you hit. In other words, you have to pull in 1,604 blocks of data in order to find all of these S86 routes. The number alone doesn't mean much, but remember our total count was about 1,700, which means that we're looking at maybe like on the average of about one S86 bus observation per block. So having to go search through all of those blocks for a needle in a haystack is pretty expensive. Note that I've run this query previously. And this will be important. I didn't want to do this live because the reorder chunk does take some time, but we'll get into some of that later. The important part to note is that when I run this on the data from March 5th, the same analysis, same SQL query, but it's hitting this this chunk that's been already reordered. We'll see that. Let's run that. So there's 1,800. Slightly more that day. If we run the explain for it, we see, okay, yes, we picked up a different chunk, which is chunk 41. And we know that we've run reorder on that previously. If we look at the number of shared hit blocks in the append here, and this is really staggering here. The shared hit blocks is now down to 30, from 1,600 down to 30. And what that means is all 1,800 of the S86 observations are now packed into 30 blocks on disk and in memory due to the reordering. And so that to the extent that your application is limited by this, by the number of blocks that you're pulling in, you can see huge performance improvements just by doing this reorder if you know you're going to be hitting a certain index. Yeah, and it's worth noting also that even with, in both cases, both in the fifth both the data on the 5th and the 6th, I have an index on both. But an index only helps you find where the blocks are. In the case of reordering, we've just dramatically reduced the number of actual blocks we need to hit, which on larger queries will give you a huge performance increase. Okay, I wanted to jump into this example. Probably not going to spend too much time on it. The one thing I did want to, one thing I wanted to point out was the window functions. What we see a lot with time series data is you don't always necessarily care about just the row that you're currently processing. You want to look at change over time, right? You want to look at a row before and see how a value has changed. And so SQL window functions allow us to do that. So window functions, also called over, you'll see it referred to as an over clause, or the over keyword will be used. Effectively, what this means is I don't want to get the geometry from the current row. I want to lag by 1. I want to actually look at the previous row and grab the geometry there. And then by comparing the two and getting the distance between them and then doing the same for time, we can compare the previous time, lag time 1, over order by time ascending gives us the previous time. We can take that difference as a time delta. So we have a distance and a time. From there, we can feed that into, we build a common table expression out of all of that, and then feed that into relatively simple SQL query that allows us to, let me run that, see, whoops. Relatively simple SQL query that allows us to look at the time and distance, and hence the speed at which each bus is traveling at each time interval. So you see this bus is reporting its location every 30 seconds, and not, as is probably common in the middle of the day in New York City, not traveling too fast. We're looking at mostly single digits and low 10, 20 miles an hour, which if you've ever driven around New York City, that's probably pretty close. So this is, this ability to do window functions where you can sort of look back and forward through the rows in order to do, to get a sense of what happened before and after, is really helpful for building sort of rolling averages or things like that. So calculating speeds is a great example. And then finally, this is sort of a miscellaneous one, but one I think is pretty important to look at because it highlights, let's see if we run that. It highlights some important things about the structure internally of Timescale that you need to be aware of when we're sort of tuning our application. We started out here, let's see, we started this on the January 9th, I believe. So you see each of these chunks. This query here will allow us to look at each of the chunks for that's sort of behind the MTA hypertable. The first month of its operation, we were looking at 1 week chunks. So we would store everything for a week in a single chunk. And if you notice, the total size here is growing to 26 gigabytes. And what was happening here was we're running on a machine that was 16 gigabytes, if you recall, of RAM. So this data set is not able to fit into memory, which was causing a lot of performance problems. And luckily we noticed this, and also luckily Timescale has a way through the set chunk interval function to adjust the chunk interval of a hypertable. So at this point, I'd realized my mistake, gone in, changed it, and then so right around the 1st of February, we started into single day hyperchunks. So with that change, we're able to store everything into about 4 gigs, which fits comfortably into memory, and see much better performance, especially on sort of real-time queries where we'd expect the most recent data to be hot in memory. So let's see, switch back. That's it for the SQL portion. I'm sure we'll have some questions later, but I think I'm going to hold the questions till the end and just jump back in to our slideshow. Another thing to point out, I've been using pgadmin 4, but there is a rich ecosystem of tools available that speak to Postgres and that speak to Timescale. One of the ones I've been using a lot with this data set is Qgis. It's a Geographic Information System software, free and open source, available at qgis.org, that has really nice hooks into PostGIS data types. So it can take any query that returns a geometry and map it along with other geospatial data to sort of give you context and really build out a nice map if that's what you're going for. Another thing that's another interesting point, along these same lines, any language that talks to Postgres can talk to Timescale. And so things like doing time series analysis, more advanced time series analyses in R. We have a great tutorial on our documentation about using R for forecasting. And so this is another example where we could use Timescale to do sort of the pre-processing, get all the data set and ready for an analysis like this in another software package. So this is just another example where Timescale fits in really nicely with sort of the data science world. And in this case, I highlighted this. I highlighted this, which was kind of interesting. This is the 3-day weekend here. We can see President's Day. Doesn't show up as a spike. So you can actually get some sense for the weekly and weekend trends of the bus routes, along with seeing anomalies like holidays and things like that. So this is a really rich data set for doing things like forecasting, which check out that tutorial if you want to learn more. All right, that's all for the sort of the application side. Of course, there's a lot more examples. I don't have time to go into all of them, but there are plenty. So we just sort of touched the surface, but I want to get into how we manage this data. In other words, how we keep it running. There's not necessarily any good to having a data system like this unless you keep it going and running smoothly. So here we see another representation of the reordering that we talked about. Just to reiterate some of these points, you see the newest data coming in roughly in time order. It's coming in as the data is inserted, which in time series is generally roughly time order. Then the older data, you see that being reordered by device in this case. Sort of in our case, we reordered it by route ID. But the idea is that you can safely and atomically reorder these chunks according to the common queries that you're going to be hitting against them, and really optimize for those. The key point here is these historical or older chunks can be reordered completely safely and atomically and without blocking writes on the front of the table. So in other words, you could be reordering the rest of your table while you are still ingesting data from more recent observations. And there's no locking, it doesn't block. And so this is a really efficient way to sort of behind the scenes make your data a lot more efficient. And this is the result, and this is a little bit more striking in terms of the time it took. But this is just another example. We were searching for a specific route ID that hit 20,000 blocks in order to find all those, and took 12 seconds. After reordering that chunk, running the same query only hit 250 blocks. orders of magnitude less, and took 3 milliseconds versus 12 seconds. So in certain cases especially where you have sort of high cardinality data and you're doing equality checks, where route ID equals something, and you really need to sort of search for that needle in the haystack very quickly, this reordering is incredibly efficient. And of course, we need to have this happen on the back end. So one of the new features in 1.2 is this reorder policies, which allow you to sort of declaratively define that, hey, I want this hypertable, MTA, to be ordered by this index. And what will happen is as the data comes in, and sort of new chunks get created to deal with the more recent data that's coming in, those historic chunks on the back end will be completely reordered according to this index without blocking the front. So that's really the key here, is that we are not doing we're not locking the whole table here to reorder it like with Postgres cluster, for instance. We are reordering it completely on a live system and setting a policy to do so that we don't need to have any manual intervention in order to get that to happen. Similarly, the Enterprise Edition in 1.2 comes with a drop chunks policy. And so this is really helpful if you have and want to enforce a data retention policy. In other words, I want to only look at data, I want to only keep data for half a year, for instance, and then you have some other archival mechanism. This, keeps you from running out of disk space, and it allows you to really sort of make it a little bit more deterministic in terms of how much data you're going to be storing, and forces you to sort of think about how you're going to deal with historical data. All right. So coming back to this slide, sort of wrap things up, we're not just building a database here. We're building a whole system for working with time series data. And so there's many challenges, on all sides, the data ingest side, the data management side, the application side. And I think the database should help you out. And that's what TimescaleDB is trying to do here. We feel that it fits really nicely into the middle of this sort of architecture, sort of helps with the full range of engineering challenges, whether you're coming at it from a DBA perspective or data engineering perspective or data science or application developer. There's really something here in Timescale to help you out on all sides. So that's what I've got. Thanks everybody for taking the time. I really appreciate everyone who's taken the lunch break to listen to this. And the code for all of this is available on GitHub. And with that, I will open the floor to questions. Is the reorder on one index only? Yes. Currently, you can reorder by any index you want, but it is sort of an expensive operation. So you need to sort of think about what index is going to be hit the most. And the way I do this is the same way I would think about adding indexes in the first place, which is to say, find the real bottleneck in your application. And if it happens to be, you put an index on it and you say, okay, well, it's still a little bit slow. What can we do to speed this up? And again, the reorder is on one index only, so you are like trading off one type of query against another, and so you have to sort of make that decision up front. Yeah. What are some other alternatives to pgadmin 4? There are plenty. If you search on Google for Postgres, Postgres front end or Postgres GUI or something along those lines, there is a wiki page on the Postgres site which has several dozen options there. pgadmin 4 tends to be the best for me. A lot of people like, there's one called dbeaver, and of course there's just the command line shell pSQL client, which I tend to use a lot of as well. But yeah, there are a lot. I think the Postgres wiki is the most comprehensive list of those, but they all have pluses and minuses. What are the implications of not having contiguous time buckets? Right, so we had looked before. I think one of the implications is the application has to account for this. If it's looking at your data as a continuous series of observations, and say you want to graph it, a lot of times your application needs to either assume that the data is sort of fully contiguous in that way, or you need to do the work on the application side in order to make it that way. By doing the analysis on the server side, we're able to do the analysis close to where the data is, which gives us a lot of efficiencies and reduces the complexity in your application. So you don't have to sort of deal with it when you're graphing. You don't have to say, well, how do I deal with a couple skipped gaps in my time series, or when you're analyzing it. This just allows you to not have to worry about it. Let's see, what kind of storage am I using on this demo? That's a good question. I didn't go into it here, but we are using, let's see, NVMe disks on AWS. So these are fast SSD drives that are, I think I have it in a RAID 1 configuration, and using ZFS, which is a file system that allows you to actually do on-the-fly compression, which is what I'm doing here. So we're seeing about a 3x compression, which helps a little bit actually on the I/O side, speed up I/O a little, and certainly helps with keeping the storage requirements low. Let's see, give examples of SQL queries that might be slow for TimescaleDB. Yeah, okay, so this question is what SQL queries might be slow for TimescaleDB. The SQL queries that would be slow would tend to be the ones that are like select star from everything. In other words, if you're not really using any of the advanced filtering or aggregation or time bucketing features, if you're just sort of pulling raw data off the disk, it's only going to be as fast as your disk. And so in this case, we have several hundred gigabytes of data and several 100 million rows. So if we were to just do a select star for the month of February and try to do all this stuff in application space, we'd be looking at pulling gigabytes of data over the network, and that tends to be what slows timescale down quite a bit. And that's not really a timescale thing, it's more of just a network thing. It sort of depends on your disks and your network, but in general, you want to aggregate the data down in the database engine as much as you can before sending it over the wire. All right. So what are some other use cases for the latest TimescaleDB features? I think this is a great question. I think, given this example, we're looking at, we were looking at the window functions to determine speed. I think you could do some of the window functions over a time series or time bucket queries, which would allow you to really do like a lot of cool moving averages and sort of get a sense for trends in your data. This would be really useful for things like IoT sensors, or you're looking at temperature over time, things like that. I think there's a lot of really good potential use cases for this. If you're looking at the time bucket gap fill functionality in particular, not all data is going to be coming in regularly, and especially if you're doing something like an event sourcing application where you really have irregular events, the time bucket gap fill is going to allow you to aggregate to more meaningful structures and get you much further along the way to analyzing that data. So what are the best practices in regards to queries which hit multiple chunks? Chunks that are not in the most recent. I mean, most queries will hit multiple chunks unless you've sort of carefully crafted them only to hit one. The chunks that are not the most recent will be loaded into memory. So I would say it depends on your application side. If you're always searching for the most recent data, if you're always querying on the most recent data, then that most recent data will already be in memory in the shared buffers. It's where you start to have to go back and do historical queries. So that I think one of the things we've seen some people do is sort of split their database up into like an operational write-only node, and then use Postgres streaming replication to build sort of a query replica, a read-only replica, that they can do some of the more historical queries on that that might, that might make some of the that might conflict with some of the real-time queries. So there's a lot of things you can do with setting up read-only replicas if you're interested in like having a system that can do most recent query and historic queries at the same time very efficiently. That's one option to look at. And we'll be following up on Thursday with a recording of this. So keep an eye out on the webinar webpage for that. Great, and with that, I think I'll sign off. Take care, everyone.